All right, welcome back. Today we're going to do something a little different. Instead of just breaking down a discovery, we're basically going to follow a recipe. Yeah, a recipe pulled straight from a theoretical physics paper for a totally revolutionary new kind of quantum device. We're talking about a microscope that's designed to see the invisible forces of the quantum world. So let's get cooking. So, what's the big problem we're trying to solve here? Well, it's this. The universe, at the tiniest scales, is just humming with these incredibly faint electromagnetic fields. And being able to measure them, that's one of the huge frontiers in science right now. I mean, how on earth do you build a sensor that's sensitive enough to actually see forces that, for all practical purposes, are completely invisible to even our best tools? Well, a new theoretical paper lays out a really detailed blueprint for how to do it. And that's why we're going to treat it like a recipe. We're going to walk through the 3 key ingredients you need to build this thing, and then we'll get to the taste test, the very specific experiments they have designed to prove whether this whole recipe actually works. Okay, let's get into it. Ingredient number 1. And it's a material you've definitely heard of, but we're going to prepare it in a very, very special way. We're starting with graphene. Yep, that amazing 1-atom-thick sheet of carbon. But we're about to supercharge it to do something truly extraordinary. So what's graphene's superpower in our recipe? It all comes down to these things called plasmons. The easiest way to think about them is as these coordinated, wave-like ripples made up of all the electrons moving together on the graphene surface. And just like a magnifying glass can focus sunlight into one tiny, intense spot, these plasmons can grab incoming energy and concentrate it like you wouldn't believe. And just look at how effective this squeezing action is. It's kind of nuts. We start with a terahertz light wave, totally invisible to our eyes, by the way. Out in empty space, its wavelength is pretty long, about 85 micrometers. But the moment that wave hits our special graphene, it gets converted into a plasmon ripple with a wavelength of just 4.5 micrometers. That is an incredible amount of compression. Yeah, that's right. It's a compression factor of about 20 times. So right off the bat, before we do anything else, we've already taken that energy and crammed it into a way, way tinier space. This is the first absolutely critical step for amplifying a signal that would otherwise be way too weak to ever notice. But like any good recipe, you can always add a little something extra to really make it pop. In this case, the recipe calls for doping the graphene. Think of it as adding chemical seasoning. By sprinkling in a bit of lithium and nitrogen, we do 2 key things. First, we perfectly tune the graphene so it resonates with our terahertz light. And second, we pack in even more electrons, which makes those plasmon ripples even stronger. All right, on to ingredient number 2. And honestly, this is where things go from clever to kind of mind-blowing. We're not just using a flat sheet of graphene. No, we're etching a very special, almost magical pattern into it. And this pattern is designed to amplify our signal to a whole other level. What we're talking about here is a fractal. And if you're not familiar, a fractal is just a pattern that repeats itself at smaller and smaller scales. Just think about the beautiful, intricate shape of a snowflake. Or maybe even better, think about those Russian nesting dolls where each doll you open has a tinier version of itself inside. We're using that exact same principle. Okay, so check out how this cascade works. It's just brilliant. The energy from those plasmons we made, it flows into the largest gap of the fractal pattern. Then the geometry itself funnels that energy down into the next smaller gap, which concentrates it even more. And this just keeps happening, level after level, a cascade of amplification, until all of that initial energy is squeezed into the very last tiniest gap, a space that's only 1 to 5 nanometers wide. So, what's the payoff for all this clever geometry? 100,000 times field amplification. And get this, that's a conservative estimate. By combining that initial plasmon squeeze with this fractal amplifier, we have literally taken a signal that was a faint whisper and turned it into a concentrated roar. Okay, recipe check. We've supercharged our graphene. We've used a fractal to create this insane hotspot of electromagnetic energy. But how do you actually measure it? How do you stick a probe in there to see how strong it is without messing the whole thing up? For that, we need our third and final ingredient, an unbelievably sensitive quantum sensor. We're going to use something called a nitrogen vacancy center, or an NV center for short. Here's what it is. Imagine a perfect diamond crystal. Now, just imagine you pluck out one single carbon atom and replace it with a nitrogen atom.
And then you leave the spot right next to it totally empty. That one tiny atomic scale flaw, it creates the perfect little quantum compass. It's incredibly sensitive to what's going on around it. In fact, its quantum state is so delicate that it can literally feel the buzz from that amplified field we've created in the graphene right next to it. So we take this little diamond nanosensor and place it right at the focal point of our fractal, and that's how we read the result. So here's the key. That super strong field from our graphene device doesn't break the sensor, it just gives its quantum spin a little nudge. This nudge is what scientists call a phase shift, and it's a tiny but very precisely measurable change that tells us exactly how strong that field is.
So you might be thinking, okay, this is a really cool recipe on paper, but is it just a theoretical fantasy? And the best part is, no, not at all. The paper doesn't just throw the idea out there, it gives a clear, practical roadmap for how to actually build this in a lab and prove that it works.
This is what makes a scientific theory so powerful. It's not useful unless it makes very specific predictions, things you can actually go out and test in the real world. If your experiments match what you predicted, your theory holds up. If they don't, well, it's back to the drawing board. And this paper lays out some really specific fingerprints the experiment should have. For instance, the signal should flare up only at that specific terahertz frequency we tuned the graphene for. And obviously, if you build a device with even smaller gaps in the fractal, you should get a much, much stronger signal. But there's one prediction that's the most important of all.
And here it is. This is the big one, the absolute smoking gun. The theory predicts that if you double the power of the terahertz light you're shining on the device, the signal you read back from the diamond sensor shouldn't just double, it should quadruple. It should scale with the square of the power. This very specific, kind of weird relationship is the unique signature that proves this special amplification effect is the real deal, and not some other simpler thing happening. And this chart really shows you why this is so promising. The authors actually did the math. They calculated how strong that signal, that phase shift, should be, and then they compared it to all the random background noise you'd expect in any lab. And look at that. The predicted signal is about 5 times stronger than the noise. That means it should be clearly, easily detectable with the technology we have today.
So there you have it, the complete recipe for a quantum microscope. The ingredients are understood, the steps are laid out, and we even know exactly how to test if we cooked it right. If this really works, it blows open a whole new window into the nanoscale, and it just makes you wonder, right? What other invisible forces and bizarre quantum effects are just waiting out there for us to finally build the right tool to see them?